come with a message from Sarah, and this is verbatim. She tried, but she can only be so high at school. That's what she wanted me to let you know. So she will not be here today.
That's understandable. Is her shirt?
I think it's unacceptable, but she's got to take more painkillers.
Start writing. The surgeon was like, "Oh yeah, you can like drive home."
Dang.
Not like from the surgery, but like you can start driving immediately. And she's like, "Can I?"
I hope it went well. I hope it fought his. I'm really excited, like Coffee Pot Crater. No. It's like, it's in that same, like, it's actually within the shuttle area for the Oahu. Okay. Like just kind of southwest of Jordan Valley, and I think Jordan Valley. Yeah. Okay, yeah, cool. I'm excited to hear what recommendations you have, because I feel like you'll have recommendations that are not in books or on the internet. And you know, like, I want to like go see cool plants. Yes. Your favorite spot? Yeah. Where you go when you well, when you have a day to like do not work. That makes me
I just realized I forgot my glasses today, and I cannot see.
I was wondering if that was what happened. Do you drive or walk or?
I drove, but I had my sunglasses, so I was already down the road and started putting my sunglasses on. But I didn't think about what happens when I need to see the floor.
That's not hard. That's really hard.
I was gonna be amazed, like, dang, how'd you drive without glasses? Like, I would not be able to drive.
Oh, you know, just hit a couple speed bumps. It's weird that they have those on iPad.
So, Professor, are we doing makeups on it, or like what's happening with that lab?
Yeah, we're doing the titration lab today.
So we're just gonna move all our labs back on.
Because this was a blank week anyways. So we weren't supposed to have lab. All right, let's go ahead and get started. And so just a reminder, today's kind of, I'm calling it makeup day, I guess. So just a reminder, everyone from Tuesday who missed out on their lab will have lab today. So if you remember from the syllabus, there was not supposed to be any labs this week. I just built it in as a buffer. But obviously, last week, since we missed class, we have to make up today. So we'll do the acid titration lab. Yeah.
So this is the lab that we missed.
Yeah, so this is from last Tuesday. And so people came in on Thursday, or the regularly scheduled Thursday people did it last Thursday. And like I mentioned last week, so I think it's both pre-lab question 7 and post-lab question 7. I said hold off on those, so hang on to your labs. And we'll go over the calculations next week, so I don't muddy up your brains with stuff right before the midterm. So I'll go over all that, but everything else you can do with stoichiometry. And then I didn't get any emails about making up lab today, but I wanted to make up any other lab, so other lab makeups. So if you missed another lab, talk to me about it. We can try to make it up, squeeze you in today. I'd rather not do it on Thursday just because we have the midterm going on, and I'm trying to give the stockroom some break from us. And let's see, and also if you missed any quizzes, today would be a good day to make that up, either after class, so during lab or whatever, or I can always send them to the testing center as well. Just, again, check in with me. So try to get caught up as we reach our midterm, so we're not falling behind. And let's see. Also, if you have any incompletes from like last quarter, I would also work on those. So again, this is a good week. Come see me, come make appointments with me. I'm available. So remember, I'm pretty available this quarter. So you can meet with me over Zoom, in person, whenever. Just email me to set up a time or talk with me in class. All right, any questions before so I said we had to finish up chapter 16 really quickly, which hopefully won't take too long. But are there any questions before we get started? Yeah.
Are there any notes allowed on the midterm?
Yes, so it'll be open note, just like everything. So you have all your notes. You can use your notes from the review today. Other questions? And of course, even though it is open note, open textbook, I encourage you, have your periodic table with your cheat sheets, your handy formulas, so you're not, spending the whole time trying to read the textbook during your exam. All right, so let's finish up chapter 16. And so we left off, so now we're looking at different types of solutions. And so now let's look at Raoult's law for volatile solutes. And so this is in a specific case where you have both the solvent and the solute can evaporate. And so that means that at any point in time, both molecules can be found in the vapor phase, again, thinking about that equilibrium. And so in an ideal solution, the solute-solvent interactions are equal to the sum of the broken solute-solvent interactions and the solvent-solvent interactions. And so effectively, the solute is diluting the solvent. And so all this means, again, this is in an ideal solution, that your pressure total would be equal to your pressure of your solute. Again, if it was a liquid, volatile solute, and then your pressure of the solvent. And so just like we had seen in our other chapter, in our previous notes, so we said that our pressure then of our solute, so we said, remember that the vapor pressure of a solution is always less than the pure solvent. And so just like before, it's just equal to the mole fraction. So you have to solve for the moles of your solute over the total moles. Then you just multiply it by the ideal pressure. So this is a pure solvent. And then, of course, your solvent, same thing. You would find your mole fraction and multiply it by the vapor pressure of your pure solvent. And again, this is what you expect for an ideal solution. And so usually you assume that you have an ideal solution.
What instances would we have a non-ideal solution?
So let's look at that right now. So let's look at these different scenarios. And so this is just a graph. And so this is, the first part is just kind of what we expect ideally. So you have your component A, and so here's a vapor pressure. So if you have obviously 0 of component A, it's not contributing anything. We have 100% B, and so all they're doing is adding these vapor pressures to give us this nice straight line here. And so now let's answer your question and where those deviations would occur. And so we're saying if the solute-solvent interactions are stronger or weaker than the broken interactions, the solution is non-ideal. And so if you have the case where your solute-solvent interactions are stronger than either the solute-solute, so either within itself, and the solvent-solvent, so stronger than either one of these solutions by themselves, then the total vapor pressure will be less than predicted. And so that kind of makes sense. So if your solute-solvent interactions are stronger than either the individual components, then that's going to lower your overall vapor pressure. And so that's just what's shown in this second graph. And so you can see the ideal kind of curve is dotted, and then this is the actual vapor pressure. And so you can see the deviation. Or the last case is if you have solute-solvent interactions that are weaker than either the pure solute or the pure solvent, then your total vapor pressure will be more. And so you would get something that looks like this. Again, you have your ideal line, and your vapor pressure of your solution is above that. And so you would never be expected to, like, just given, I would never say, like, given these two compounds, what's the graph going to look like? So let's look at what you might actually be given. So here's an example problem. So we have a solution that contains 3.95 grams of carbon disulfide, 2.43 grams of acetone, and it says the vapor pressures at 35 degrees Celsius of pure carbon disulfide and pure acetone are 515 torr and 332. And so assuming ideal behaviors, calculate the vapor pressures of each component and the total vapor pressure. So we'll start with that. So I'll let y'all loose in a second to calculate that. And then what we're comparing it to is we have to have some sort of experimental real number, because again, we can't just predict this instinctively. And so it says experimentally, the measured total vapor pressure is 645. And so now we can ask, is it ideal? And then we'll kind of compare the strength. So let's start with the first part. So see if you can at least get started on what we have to do. So let's at least start going through this. So what do we have to do first? So find moles, so let's start with carbon disulfide. Does anyone have the molecular weight for that? Yeah, Vaughn.
With 3 sig figs, it's 76.0 grams.
76.0 grams, is that roughly what other people got? Okay, just doing a quick sanity check. So we can do 3.95 divided by our molecular weight to give us moles. And then does anyone have the molecular weight of acetone? 58.08. And that sounds right to me. So looking for at least some not awesome. And so now we can find moles of each. So did we get like 0.052 moles for carbon disulfide? And let's see, what do we get for acetone? How many moles? Do we get about 0.0418? See, at least one nod. Awesome. Just looking for more confirmation. And so now we have moles, so we can find our mole fraction of each. So I'll just do carbon disulfide first. And so put moles of carbon disulfide on top over our total moles. So do we get 0.554 for a mole fraction? And don't forget that's unitless. And let's see, do the same thing now for acetone. We probably could have also subtracted 1 minus this to give us a mole fraction, since there are only 2 components, but I'll do it both ways. And so I guess we got 0.446 roughly. And so now our total pressure is then, so we have our CS2 with that mole fraction, and let's see, what was its CS2 was 515 torr, then plus our mole fraction of acetone times its partial pressure, so 332 torr. So do we get a pressure of 433? Yeah, I see 1 nod, 2 nod. So 433 torr. And so first question, so is our solution ideal?
No.
So no, not ideal. And so just to remind ourselves, the actual was 645. And so now we're saying that our actual vapor pressure was higher than we expect. So what does that tell us about our interactions? Yeah.
The interactions between solute and solvent are weaker than the reactions, interactions with the broken interactions.
Exactly. So our solute-solvent interactions are weaker than we would expect from an ideal solution. So they're weaker than either the solvent-solvent or the solute-solute. And because they're so much weaker, that makes the actual one, again, much higher than what we predicted. Excellent. So questions on that and how you might be asked about it on an exam? And so again, I would never give you two substances and say like, oh, would the actual pressure be higher or lower? You know, you have to have some sort of data for it. Yeah.
I have a question. Why are we why are we multiplying the mole fractions by the partial pressures to get the total pressure?
Because you have to multiply them, because we're trying to get like the total vapor pressure. So then we're just multiplying them by the vapor pressures at that temperature we're looking at, so we can get the vapor pressure at that temperature. Did that answer your question, or? Maybe I didn't understand.
I was more saying, so I get the fact that you have to add the two together to get the total pressure, but why are we, and why is it not just the pressure plus the pressure instead of the pressure times the mole fraction plus the mole fraction times the pressure?
Because we have to take into account, because remember the whole, like, if you make a solution that lowers the vapor pressure.
Yeah.
So that's all that we're doing here. I was just trying to find. Yeah, so it's related to this whole factor, except we're specifically looking at a slightly different case, because this is for like everything. This is really general. But now we're just kind of looking at it more specifically where we have a volatile substance. So all that means is like normally, right, if this is our solute, we don't always have a liquid solute. It's usually a solid. But in this case, if we're doing two liquid-liquid things to get the vapor pressure, that's where you have to do the mole fraction of each.
Gotcha. I see.
So just to kind of do my own sanity check, 433.4, you're saying is weaker than?
Well, this was the ideal, right? So this is like ideal scenario, what we calculate. So yeah, going back to these graphs, we calculated this pretty picture because that's all we can do. And then you're just comparing it experimentally. Was it higher? Was it lower? The actual one. And so we found the actual is lower, meaning we're at this scenario where we have weak solute-solvent interactions. Other questions on that one? All right, let's look at the last little bit of this chapter. And so now this is just dependence of solubility of gases in water. And all it's related to is basically this formula. And so this makes sense. So the larger the partial pressure of a gas in contact with the liquid, the more soluble the gas is in the liquid. And so you can kind of imagine this with soda. So they have to have it, you know, highly pressurized so they can get that CO2 actually dissolved in there. And of course you open your can up of soda or whatever, sparkling water, and you get that fizz, since that CO2 is of course now released under pressure. And so this is one of those ones where again, you just pay attention to your gas constant. So we have our solubility of our gas is directly proportional to the partial pressure of that gas at that temperature. And so every gas has a different Henry's law constant, so KH here. And then notice the units, so as always, watch those units. So in this case, they're given in molarity, so big M, so that's molarity. per ATM. So again, just watch that. It's not too difficult. And so our KH for CO2 is 3.4 times 10 to the negative 2 molarity per ATM. So depending on how much gas you want solubilized, that's how you determine what pressure. And so the funny thing, too, about gases is, so gases have a lower solubility in water than ionic and polar solvents, since they're nonpolar. So that makes sense, right? So gases, they're nonpolar. We know water is really polar, so they don't tend to dissolve well. And then this is also odd. So for all gases, the solubility of the gas decreases as the temperature increases. So I would put on there, right, opposite of solids. So in general, there are some exceptions to this temperature solubility rule, but in general, and I'm sure you've seen this, you heat something up and it becomes, in general, more soluble, except with gases. So it's the exact opposite. So you heat it up, and then that basically just causes all the gas to escape from your liquid. And so how can you make the solvent hold more solute? So we can always vary the temperature or the pressure. So solutions can be made saturated or supersaturated by changing the temperature or pressure and allowing the system to go back to the original conditions. And so some solutes, instead of coming out of solution when the conditions change, then you get a supersaturated solution. And you've kind of seen that, I think it was it in this class? Maybe I'm thinking of the wrong class. Yeah, I'm thinking of the wrong class, never mind. But just like if you make I always think of rock candy, you can dissolve a bunch of sugar in water, you have your supersaturated solution, and then you could eventually get that to crystallize out. And so supersaturated solutions are unstable and lose all the solute above saturation when disturbed. So you could shake a carbonated beverage, and obviously that's why you don't open a can after you've shaken it, because you've kind of disturbed it. But if you were to, right, it all kind of fizzes out since that CO2 is all escaping. And so that's why kind of warm soda fizzes more than cold soda, since again all that carbon dioxide is leaving at those higher temperatures. And so now we can do our little example problem. So what pressure of carbon dioxide is required to maintain the CO2 concentration in a bottle of club soda at 0.12 molarity at 25 degrees Celsius? And so you'll want that data. I'll just copy the problem again. All right, so let's go over this problem. So it's fairly straightforward. So we have our solubility of the gas, and so it's telling us we want to maintain this concentration. So I'm just going to rewrite this for a second. So SH is equal to our constant times whatever pressure, and so we want it to be at 0.12 molarity. Oops. So we're trying to solve for pressure, and then we just reference our constant, and again, watching the unit, so it's given in molarity per ATM, so we're solving for pressure in ATM. That will cancel to give us back molarity, which is what they gave us, so that looks all good. So I need to copy this, so 3.4 times 10 to the negative 2. And so now we just have to divide, so 0.12 divided by our Henry's gas law constant. And so we get 3.5 ATM. So is that what everybody got for that one? Awesome. Nods. All right, so that takes us to the end of chapter 16. So any last thoughts on 16 before we move on to midterm review? I'm sure that's what everyone is really excited for.
What was your response?
It's just whatever relates how much pressure to concentration to give you like how much amount is solubilized in gas. So on an exam, you'd have to be given Henry's gas constant. I wouldn't make you hunt for it, but in real life, you know, you might have to hunt for it, watch the units that it's given in, all those good sorts of things. So one comment before I dive into our review. So I noticed that from the last quiz, there's still some confusion of like London dispersion versus dipole-dipole. And so the question asks, like, give me an example of some compound that has London dispersion and dipole-dipole, but no hydrogen bonding. And so quiz. So it's some sort of molecule that has London dispersion and dipole-dipole. No H bonding. And so the first thing I wanted to clear up is, yes, all molecules do have London dispersion. So I did get some confusion from people of like, doesn't everything have London dispersion? And like, yes, that is absolutely true. And so you could really have picked anything for that. The only thing is, so don't pick any ionic compounds, right? Those aren't molecules, so those would not be included. But then we have to pick something with dipole-dipole. So what does that mean if it has a dipole-dipole interaction? What are we looking for? Yeah, so basically it has to be polar. So we have to find some compound that's polar. And so, for example, somebody gave me PCl5, except what's the problem with PCl5? So it's nonpolar. So this is, right, so it's nonpolar. So of course it has London dispersion, because everything has London dispersion. But this would not qualify since there's no dipole. And so you could have picked anything else that falls under this, again, as long as it doesn't have H bonding. I'm trying to think of what people gave me. Actually, this chloroamine was a good one. So this could have worked. I also saw a cool one of iodo-chloroform. So this is actually extremely polar. I honestly didn't even realize how polar this was, but so this would be a good example where it has a difference in electronegativity, but like chlorine, right, that's nonpolar, so that wouldn't work. But something like that. And then obviously don't pick like water or something with hydrogen bonding, so that has H bonding. Same thing, right, ammonia, that wouldn't work, H bonding. That's why I like this chloroamine example that somebody gave. That was pretty cute. Yeah, I like that one. I like this one. And people gave me other great ones as well. Those are just what stuck out.
So I thought London dispersion forces were only for non.
That's when we mainly look at them, but they're technically in everything. So everything can make like a temporary dipole. It's just they become so insignificant with like hydrogen bonding that it doesn't even matter. So it's like, yes, water has London dispersion forces because it exists and it can still create temporary dipoles, but you're right, the most dominating force is hydrogen bonding, so we don't even care about the London dispersion. Because remember, the London dispersion just depends on the size and the shape. And so by London dispersion, water should have an extremely low boiling point. That's what we would expect, right? That it should be a gas if we were just looking at London dispersion. But obviously we know that's not the dominant force. Instead, it's hydrogen bonding. Good. Any other questions? Good questions. All right, so let's look at your exam, or I'm looking at your exam. So I think it's pretty much in its final form. The first part is like 7 multiple choice questions. I don't want to give it all away. Oops, what am I doing here? So what is going on in this leg of a phase change diagram? What? Melting potentially, or would it be melting?
Heating a solid.
Heating a solid.
Dan TJ said, might drop into beer works for a beer for the
You mind if I mean, it's my buddy.
As long as you're bringing us all beer, yeah.
Yeah, it's everybody's 21.
Sweet. So yes, heating a solid, excellent. And then what happens on these plateaus? So phase change, excellent. And so heating a liquid. Heating a gas. So not too crazy. And then, so let's do another example now. And so again, I'm just like looking at the exam and doing problems that are close or representative. So if we have a 0.3 molality solution of iron 3 chloride, what is the colligative molarity? Or molality, sorry. Molality. So take a minute or two. What do you have to multiply it by? So what's the key with this question? What am I getting at with? So what does it mean by colligative molarity? And what's the relevance of this iron trichloride?
Is it something with the Van Hoff factor?
Yeah. So then how many ions would we expect this to make in solution? 4. And again, we're just assuming ideal. So 1 equivalence of iron plus 3 of our chlorides. And so that means even though I put in a 0.3 molal solution, I get 4 ions. So we just take our molality times 4. And so what do we get for our colligative molality? So then we should get a 1.2 molal solution, effectively, of ions. So that's just a multiple choice question. And so there may be a little bit of trivia from like your inner chapters, but I picked questions that you could get the answer just by not reading the chapter. And so what I mean by that is like check to see that the formulas are correct, you know? And so for some hint, so silver only makes 1 plus ions. So you'd probably want to, you know, balance the charges, make sure that the formula is written correctly, and that's probably your right answer. Let's see, other hints. There's some other trivia thing, but I'll just remind you, right? So xenon is at least one of those well-known examples that we've talked about that makes compounds with fluorine. So that may be on there. And so what's a network crystal? That's part of your multiple choice. What are some examples of network crystals?
Is that like metallic crystal? I'm just thinking.
I don't think so.
Okay.
Well, what's an example of a network crystal? We've talked about a few of them. So salt would just be, that's more like a ionic compound. What are other repeating units? Yeah, that's the one. So that's at least the big one that we talk about. So diamond is an example of a network crystal. So network crystal should be some sort of covalent compound. And so that's different because you mentioned the metallic crystal. And that's just going to be, again, like the sea of electrons. So just like a metal. But yeah, so this would either be diamond or silicon dioxide. So something that's defined formula, repeating units. So that's good. And then there's something about boiling points. So which has a higher boiling point. And we'll just do one example. So ethanol versus so without asking the internet, which one of these would have a higher boiling point, do you think? Acetone, but it doesn't matter too much what it is. You should just be able to look at it. Yeah, so the hydrogen one. So exactly. So this would have been a good example for your quiz, potentially. So it has London dispersion, and then it does have a dipole from this CO bond. So we have some sort of polar molecule. So that means it has dipole-dipole. Exactly. And so yes, that's nice, but that doesn't compare to our hydrogen bonding of ethanol. And so we have hydrogen bonding in addition to all these, so it still has dipole-dipole and London dispersion. But again, hydrogen bonding is the dominant force in that molecule, so we would just predict, since they're relatively close in size, that yes, probably ethanol has the higher boiling point.
Can you just explain the acetone at the bottom? There's an O, and then what are the things below the O? Okay, got it. Thank you.
Sorry, I was drawing shorthand. So the next question on your exam is an MO diagram one, but I'm going to skip reviewing that for the end. So we'll skip that. And so your next question, we'll do an example if I could draw this properly. And let me draw this not in the shorthand way. There we go. So looking at this molecule, I think it's called acrylonitrile, but looking at this, so determine the total number of sigma and pi bonds. And then I want the hybridization at each carbon, so carbon 1, 2, and 3. So take a few minutes. How would you approach this? And we'll go over this. line. So I'm just going to redraw it for a second. And so you may want to do this on your exam with whatever compound you're given. And so the emphasis here is on total number, because remember, don't forget about these sigma bonds. So we have sigma, sigma, so this is sigma plus pi, sigma, sigma, and then what's this one? So 1 sigma plus 2 pi, perfect. And so now we just have to count everybody up. So 1, 2, 3, 4, 5, 6 sigma bonds plus 3 pi bonds total. Is that what everybody got? Excellent. And then what's the hybridization at this carbon 1? So sp2, perfect. So 1, 2, 3 things. So 3 orbitals mixing. What about this next carbon?
SP.
Yes, also sp2, so 3 things attached. And then this last carbon, sp. Excellent. All right, so hopefully that should be a little freebie for your exam. All right, let's try some gas law questions. So what is the molar mass of a gas if 0.214 grams of the gas occupies 1.56 or 1.56.0 milliliters at a temperature of 170 degrees Celsius and a pressure of 857 torr. So take a few minutes to do that, and then we'll go over it.
And this community was an RT, right?
Yeah. Do you have an answer yet? How's it coming along? So I think someone had said earlier that this was a PV equals nRT question. And so we need to solve for moles then to figure out, well, how many moles is this 0.214 grams? And so of course pressure, we had to convert to ATM. So divided by 760. So what do we get for pressure? 1.128. And then our volume has to be in liters. So 0.156 is equal to, so solving for N, then our gas constant 0.0821. And then what's the temperature in Kelvin? You said 433? Oh, 443. Thank you. I was feeling lazy. And so let's see. Oops. So do we get 0.00484 moles? Okay, see some nods. So 0.00484 moles roughly. And so we could just divide, or sometimes I like setting up a proportion for my own sanity. So now we know that 0.214 grams is equivalent to 0.00484 moles. And so if I want 1 mole, what is that equal to? Yeah.
I forgot, do you have to convert the milliliters to liters?
Yeah.
Oh.
Yeah, so if we're using the PV equals nRT, remember everything depends on that gas constant. So since the gas constant is for liters, then yeah, you have to be in liters. I'm not sure if there's a version where it's in milliliters, but you probably don't want to confuse yourself. And so then we can just divide, so 0.214 divided by our moles we found. So do we get a molecular weight of 44.2 grams per mole? Yes, no, thumbs up, sweet. So 44.2 grams per mole. So let's do another one with heat capacity. So we're going to use not water. And so instead we're going to look at acetone. And so some relevant points that we need. So the freezing point for acetone is negative 94.9 degrees Celsius. Boiling point is 56.08 degrees Celsius. And then, sorry, lots of information. So delta heat of fusion is 5.7 kilojoules per mole. Delta heat of vaporization is 31.0 kilojoules per mole. And then our heat capacity, and I may be giving you extra information, is 75 joules per mole Kelvin. Heat capacity liquid is 125. Joules per mole Kelvin. And our heat capacity solid is 90 joules per mole Kelvin. And so chemists like a nice dry ice acetone bath. And so let's see. Let's say we want to take our substance so how much energy is required to take 1 mole of acetone from negative 100 degrees Celsius, so freezing, to, and let's just say we want to take it to room temperature, so to 25 degrees Celsius. So take a few minutes. Again, there may be extra information.
What was the freezing point? 4.1?
The freezing point is 94.9. did we get an answer already for this one? Working on it. So let's at least start going over it. So what do we have to do first? So we're at negative 100 degrees Celsius. So where do we have to take it first? To what? So exactly. So we're looking at our first leg. So we need to go from negative 100 to our freezing point, because we can't do anything once we hit our state change. And let's see, the change in temperature then. So our delta T, and it goes up the same as Kelvin, so that's fine to not convert. So we have 5.1, and then using our heat capacity, and I try to make it easy for this example, so we have 1 mole, and then just watch the units, because on the exam they may be given in different units, so just watch that. So times our delta T, so remember our energy is equal to, we said mass times heat capacity times delta T, but obviously in this case we're in moles. So again, just watch that. And so heat capacity for our solid is 90. And then the other thing I noticed on the quizzes, like I think there was a question about heat change on the last quiz, and people just didn't watch between joules and kilojoules. So that threw some people off, even though their math was relatively correct. So 90 times 0.51, or 5.1, sorry, I wrote that wrong, times 5.1. Since they go up by the same amount, so you could convert it, but like the change in temperature is still the same. Yeah. So then do we get that we needed 459 joules just to bring it to that temperature? And so now we're at the freezing point. So now we probably need to do our state change. So still at the freezing point. And then what value do I need from here?
Heat is fusion.
So our heat of fusion, so that's for our melting or crystallizing. And so we have 5.7 kilojoules per mole. And we have 1 mole. And so that gives us 5.7 kilojoules. And so now we're at negative 94.7. Now it's a liquid. We need to take it to 25 degrees Celsius. So let's see, 25 minus negative 94.9. So that gives me a delta T, of 119.9. Now I can use my liquid heat capacity because it's a liquid. So we still have 1 mole times our delta T, and again times my heat capacity, it's in joules per mole. So then I get 14 kilojoules roughly, or I guess I should have rounded to 15 kilojoules. So equals 14 point, I'll round at the end. And so now the total energy, so 14.9 plus my 5.7 plus 0.459 and then I'll round to 1 after the decimal point. So did we get a total energy of about 21.1 kilojoules? Excellent. All right.
Can you go back to that?
Oh, sorry. Oh. You have questions about it or just coughing down?
Just wanting to make sure I get it.
And then let's do one more practice of another type of question. So we have a solution of a non-electrolyte. And so the osmotic pressure at 30 degrees Celsius of this solution contains 0.455 grams of compound and 100 milliliters of solution. And the pressure is 64.5 millimeters of mercury. So what is the molar mass of the compound? So not to rush you, but I wanted to get through a few more questions on your exam. So what formula do we need for this one? Yeah, the capital pi one. So which one was that called? Yeah, osmotic pressure. So this is equal to, and then do you remember the rest of that formula? So MRT. Yeah. There is a I. Sometimes that it's like dropped in and out of this formula interchangeably. But then in our case, since it's a non-electrolyte, that I is 1 anyways. So that was at least our first key point. So okay, we're assuming it's a non-electrolyte. So I'll just simplify it to that form. And remember, R is the gas constant, 0.0821. And so what's my temperature? Because we got to convert to Kelvin. 293, right? Oh no, 303. So we're at 303 Kelvin. And then we'll get to this. So we have our pressure, except we have to convert this to ATM, right? So 0.0849.
In this our book says 1 atmosphere is equal to 760 torr, and then in parentheses it just has 1 millimeter Hg.
Yeah, that. I don't know. I think it's supposed to.
Oh, I see. I say really stupid.
No, it's fine. It's just trying to say that millimeters of mercury and torr are interchangeable, but
It's written kind of.
yeah, I could see how that doesn't really come out well. And so now let's solve for molarity, because if we can solve for molarity, so we're given grams, we're given a volume, so then we can get there. But let's figure out our molarity first. So 0.0849 is equal to molarity times R times T. And you can use, obviously, the more precise gas constant. I'm just too lazy, I guess. So did we get like a 0.0034 molarity? At least see one nod. And so, of course, that's going to be moles over liters. So moles per liter. And so now let's see. So we have 0.455 grams of our compound in 100 milliliters. So we could determine how many moles this is then, or how many moles we have in that solution. Moles over liters, so times liters, so times 0.1 would give us 3.41 times 10 to the negative 3 moles, right? Since we had a 1.00 times 10 to the 2 milliliters of solution, So that's just 100 milliliters. And then I converted that to liters to give us 0.1. I'll arrow this. So from that value. And so now we have moles in our solution. We have grams now that was equivalent to. So now we can finally solve for our molar mass. And so we could just divide then, so 0.544, oops, divided by and so I get 133 grams per mole. Let me know if you got the same thing. I see some nods. All right, any questions on that one? So the last question, so we haven't gone over, so I said that question 8 was an MO diagram. So we haven't gone over that. But then there's also 2 bonus questions that are on your exam. I wanted to go over the one bonus question because it sounds difficult and it scares students, but I think you could all get it if we went over it. And so that's bonus question 13, but then there's also question 14 that's a bonus. And that's just related to 8 though. And so 14 is just basically pretty pictures of MO diagrams and then seeing if you can relate them back to your diagram, but that's why it's a bonus. So relating web MO pictures to your diagram. And so we're kind of out of time, but we have like 4 minutes, so you can let me know if you want to do the bonus, whether you want to talk about MO diagrams, or do it all and just be over time. All right, so let's do it all. So let's start with the bonus, and then we'll just talk about MO diagrams kind of at the end. So the first bonus question is, so let's say we have element X, and it has a mass, so its atomic mass is 50 grams per mole. And let's say it has a simple cubic structure. And it has a density of 3.7 grams per centimeter cubed. And so assuming it's a perfect sphere, determine the volume. So assuming a sphere, determine volume of a single X atom. And let's do it in cubic nanometers. And you're also given that the volume of a sphere is 4/3 pi r cubed. All right, so let's just do it together since we're kind of out of over time. And so how would you approach this? Just thinking about it. So simple cubic structure. We're given our density. So what could we do? And we just want to know a single atom. So what do we know about a simple cubic structure anyways? Like how many atoms are in there? So 1. So that's our key. So there's only 1 atom in there. And we also know, so we can determine the volume of some way. So we have density, we have mass. So density equals mass divided by volume. So we could find the volume of this cube maybe. And then maybe we could determine then the volume of our single X atom as a crystal. And so the key point to this is, so you want to start by finding the mass of 1 atom. So we're given molar mass, but let's just divide. So we could do 50 grams per mole. And so if we divide by Avogadro's number, that will give us our mass. So let's do that. So 50 divided by Avogadro's number. Oops. So now we have a mass of 1 atom. So 8.3 times 10 to the negative 23 grams. And so we still have our density. So density, so now we have 3.7 grams per centimeter cubed is equal to, so we have our mass. But now we need the volume. So density, mass, volume. And so if we want to get volume, we just need to divide, right, our mass divided by our density to give us our volume. So now I'm just going to divide. Oh. And so now we have a volume, and again this is for 1 little atom, of 2.24 times 10 to the negative 23rd centimeters cubed. And so if it's a cube, what's then, how can we get something useful from this? So what do I need to do next now with this information? So what's just the volume in general of like a cube? Yeah, so it's just length times width times height. And so all the edges are the same, right? And that's kind of the other key point, is the radius then for a simple body cube is 1/2 of one of these lengths, right? So what we could do is if we take the cube root of our volume, that gives us one of the lengths of our simple cubic structure, and then we can find the radius of our atom. So let's do that. So we'll take this to the cube root to give us the length of one side. And so now I have the length, or x, is 2.8 times 10 to the negative 8th and I'm still in centimeters. I haven't converted yet. And so that means that our radius is half of this for our little cell, for our simple cubic structure. So that means my radius is half of that, so I'll just divide by 2. So about 1.4 times 10 to the negative 8 centimeters for my radius. And so maybe at this point, I want to convert to nanometers, just because I'm in one dimension, and that's more for my sanity. I don't want to cube something and then try to convert it later cubed, because that's a pain. And let's see. So nanometers. So I'm going to go to my base unit first. So there's 100 centimeters in 1 meter. And I'll go back from my meters to nanometers. So 1 times 10 to the 9th nanometers are in 1 meter. So then that gets me my conversion at least. So now I have 0.141 nanometers. Again, this is my radius of compound X. And then the last thing, so it said we wanted the volume of a single atom. And we were given the formula, so now we just have to plug that in. So 4/3 pi r cubed. We have our radius for our atom, and so now we have to plug that in. So times 3 times, or excuse me, to the power of 3 times pi times 4/3. And so I get a volume of 0.0117 nanometers cubed. Is that what other people got? 0.0117 nanometers cubed then for our volume. Questions on that one? So again, it's a bonus, so don't stress too much, but I think you can get it. Just go step by step, just do 1 atom, watch your numbers, and then I didn't want to do a big diagram, but just pay attention, right, whether you have SP mixing or not. So SP mixing, you have that different order. So where you have these two, so your sigma S antibonding, and then, no, I forgot the order. And then it's the 2 degenerate ones, right? And then this one, 2, again. So that's when you have SP mixing. And then no mixing, the order is just flipped. And so this is going to be your pi bond, still sigma bonding, anti-bonding, sigma anti-bonding. And then no mixing, they're just flipped. That's sigma bonding. Again, that's PZ. Then your degenerate pi's, then the pi antibonding, sigma antibonding, And then all you do, right, is fill in the electrons. And so if you're asked to do like multiple ones, really, again, all the difference is how many electrons. And so you could use like color coding to kind of show me on one diagram or some sort of system, or you could just redraw it. And then with your WebMO pictures that you're looking for, you just want to see where like the shading either matches or is opposite. And I know it's in black and white, so try to give like some hints. If you see, you know, these big blobs, and this is all like one big shading, then that's probably some sort of pi bond, right? So, and you'll see the atoms in there, but there's some sort of atoms. I know it looks ugly. But then you can tell that's some sort of pi bonding orbital, and you just want to be able to match it to your diagram later. Any questions about MO diagrams? I don't want to take more time since we're already like 10 minutes over or more. All right, if you have questions over MO diagrams, I would just see me individually. So see me individually for any questions. Again, Wednesday you can come chat with me. And thanks again. I'm sorry we're over time. And then I will see many of you very shortly for lab.
What time is lab today?
1:30.
1:30. I'm gonna go get some coffee.
Yeah. And it's okay if you're late to lab if you need to grab some food, I understand, since we went over today.